Hi friends, this is Suresh and this video regarding to meetup event 3D ResNet for action recognitions. So I'm going to share my screen for the share the PPT. So purpose of this video, we are going to discussion about 3D resonate for the action recognitions, and this is part one. Next, we will discuss more about the deeper, but this is part one about action recognitions, about different kind of the networks, and can we retrace? Can we the three in the 3D CNN can third dimensions means here can yeah 3D resonate yeah Spatiotemporal third dimension kernel can retrace the history like ImageNet, like 2D CNN. In ImageNet, you heard about different kind of image classification tasks and image segmentations, object detection, different kind of tasks, and successfully executed. And we have a successful history about ImageNet. Similar kind of action recognition for the video analytics for video classification. We have same kind of history. Yeah, we can retrace the same history. So this kind of the discussions we are going to discuss here. The purpose of this event here. So these outlines we are going to discuss can spatiotemporal 3D CNN retrace the history of 2D CNN and ImageNet. Second thing, we are going to discuss brief about 2D CNN and 3D convolution neural network, how 2D and 3D convolution neural network differ and work. Third, we are discussing about different kind of data set for video analytics, for video classifications available publicly. Fourth, we discuss about training and inference setup, and I will show some video, some demo for how action devolution is work. So first topic, like we discussed about some 2D network and 3D networks. You hear about ImageNet dataset, you hear about 2D, and what happened in previous year with ImageNet datasets. You find that when especially in started boom in 2014, in that year ImageNet come publicly and start different kind of image classification, image tasks, and we received a significant result for the image in especially detections, segmentations, for captioning, for classifications like this. And using the ImageNet, you hear about the resonant networks, residual networks, the different kind of the depth of the network, like the layer of 122 layer, 152 layer. Here I discuss 152 layers. So in 152 layers, the accuracy level of 2D CNN reached here, and same history is like ImageNet dataset for the video in kinetic dataset. The kinetic dataset has more than 300k videos and 400 human actions available there. So similar kind of the results we found using the kinetic dataset. So I'm going to the discussion about a research paper published by a Japanese university. The paper name is Can the Temporal Spatiotemporal Third Dimension Kernel Retrace the History like ImageNet, like 2D CNN, in particular field of like detection, summarization, optic flow, video classifications, similar if we are comparing ImageNet and kinetic datasets like that. So right now what happening here? So kinetic data set right now we are the getting significant results, and it's enable the training to the deeper till 152 layers resonate and getting significant results similar kind of ImageNet dataset. The third thing, basically, for understanding, now we are discussing about how 2D CNN work, and I am not going to differ for 2D CNN because I am going to slightly deeper in 3D CNN, but I explain briefly how 2D CNN work here. In 2D CNN, for example, the one channel image, and this is a filter. So in one channel is, yeah, this image size 5 into 5, and we are taking the kernel size 3 into 3. So this is convolving the feature map 3 to this kind of incomplete image, and this kernel sliding one, like we can say stride is the one, and one by one it is sliding, and here we are getting the feature maps. In another way, in the 3D, how the 3D image will work. For example, we are three channels filters. If you will take three channel filters for red, green, and blue, then we can convolve the features accordingly. I explaining in the another slide. For example, more for three channel image like red, green, and blue. For example, this is the three channel image. The first channel is red and green and blue, and the filter also similar on three channel filter. This is for red. This is for blue. This is for green. So same kind of the, if like here stride we are taking one, and padding we are taking 0 0. I'm showing the 0 0 0 0 both sides. So this is called the padding, and it's slide two step in the slide is two, and here the convolve the features. So input is the 7 into 7 into 3. 3 means channel here, and the filter is 3 into 3 into 3, and channel is 3 because we have three channel RGB. So here we are convolving, and we are getting the output for both filters. This W0 filter and W1 filters, and we are getting results output 3 into 3 with two channels convolve. So this is the finally output for the features. So I am showing here for basic how 2D convolutions happening here. So 2D convolution happen particular image by convolution per one image, one channel. So we are not working here multiple frame. We are not working here clip of the image. So this is the brief about how 2D CNN working. Now we are going to discuss about how 3D CNN 3D convolution neural network works. So in 3D convolution neural networks, in 2D CNN we found, in 2D network we found that we have two dimensions, height and width, and in 3D CNN, we taking the third dimension, we will call temporal, yeah, we call spatiotemporal dimensions. That is called the third dimensions, and we convolve feature accordingly. And similar kind of this is the third dimensions. We can show the time, we can show the frame, right? So similar kind of the you watching here the filter also. So filter also in the third dimension also, and we are convolve the feature output also in the third dimension. So generally I explaining more, I get in another slide. So you are looking this slide also. So what happening in 3D CNN? So in basically think about it, a video. So video clip around, for example, 10-second video clip as an input. For example, 10-second video clip as an action for actions like yeah action like picking some object like that. So 10 second and 10-second video, if 30 per second 30 frame, then 10 second around 300 frames is there in particular video. So how much frame we have to took as an input for the 3D networks for convolving the features. So whatever I am discussing about the papers, that paper can with retrace the history using the 3D kernels. That papers they're discussing about 16 frame for input, and they are taking 3 into 3 into the kernel also same. So how convolving the features here, if we thinking about in similar kind of stride in 2D. In 2D we are showing the stride like stride taking the two step. In 3D, like we are taking a third dimension step, like this is the first frame, this is second frame, and third frame, right? So we taking the we took three frame, for example, three frame for the convolve, and this is the 3D kernel, this is the convolve the features, and finally the produce a one feature maps. Similarly, it slide more like for the next three frame, and it convert the features same kind like 2D, it convert the features like these features similar, it will work like that. So continuously the feature will convolve and create third feature map also create in third dimensions. So what is the difference between 2D scene and 3D scene is the third dimension. So here we are breaking on the video clips. So we have third dimension, the temporal dimension. We took the temporal dimension and convolve feature accordingly. So that is the main difference in 2D scene and 3D scene. So in 3D scene, in 3D scene and in 2D scene we are not getting the temporal 3D features, but here we are getting the temporal 3D features. So for example, we took three frames here and we are creating a feature map using the three frames. So using the three frames, we are getting the temporal features, the one temporal features. So that is the main benefit, and we are getting more information using the convolve 3D scene. So this is the main difference how 3D CNN and 3D convolutional neural network works. So that basically steps of the 3D CNN. Now we talk about the 2D CNN, we talk about the 3D CNN. Now basically we discuss about what kind of the data set available for train 3D CNN. So what is the math behind 3D science? We can discuss later. But basically in this tutorial, so we discuss about the flow, how we can train the action recognitions, we can train human activity recognitions. So I found the different kind of the data sets like ActiveNet. ActiveNet is the most popular data set, and kinetic data set, UCF 101 data set, HMDB 51 data set, Sport 1 data set. Now we are going to discuss about active different kind of the data set available for training 3D CNN, for training action recognition, for human activity recognitions, for the different kind of the networks. So here in this PPT we are looking at ActiveNet, Kinetics, UCF 101, HMDB, Sport datasets. This kind of the dataset is available. In ActiveNet dataset, 149 hours video is available, and uh, 28000 actions instance is available. Means action instance not human actions, different kind of the action is available. But if you thinking about human actions, then around more than 400, 500 around human actions is available. In similar kind of for especially human actions, kinetic data set is a very clean data set, especially for human action categories, and more than around 400 human action categories available, and 300k videos available, and average length of the dataset is like 10 second. Average length is 10 seconds, but the length of the video may be 5 to 10 seconds, 5 to 15 seconds length, maybe the video clips that dataset is available. Another kind of the dataset, the UCF 10, that is University of the Florida, that datasets there, and they also have 1300 20 video frame from extended cognitions, and this category, and HMDB sports one, and this HMDB 51 dataset also, they have lot of video, these kind of. Here, the kinetic dataset. Kinetic dataset is the most popular dataset, and we can compare the kinetic dataset to the ImageNet dataset. So in UCF, okay. So whatever comparison next we will do with this kind of data set, we have to compare, and how if we train the ResNet dataset, network. I will show some example also how they are dataset looking. So here you can see apply eye markup and blow dry hairs, brushing teeth, cutting the kitchens, hammering, and like hula hoops in jogging boats. So this kind of the actions available in this particular data sets, and jumping, and her rock climbings, and head massage, and playing piano, playing sitar, tabla, so cricket, shot, diving. So different kind of, like in different kind of data sets, different kind of the human actions is available. So but most probably what I discuss here, I in 3D CNN also the different kind of the CNN is available, like 3D C3D deep network, and Inception 3D, using the Inception 3D deep networks, and so these kind of the networks available, and for that input also very different kind of the inputs, like optic flow inputs in RGB inputs. Some people are working on the optic flow as an input to that 3D CNN, and they are getting significant results. Some people are, you feed only the RGB, and they are getting the significant results. But according to this research, optic flow and plus RGB both feeding to the network, then we can get the most significant results. Here we discuss about not that kind of instructions and this kind of network. We discuss about ResNet, because whatever in the paper they are doing the experiment with ResNet network, like ResNet layer 18 layer, ResNet 34, ResNet 15, ResNet 101, and ResNet 200. And this graph showing one is the model depth, and another is average accuracy, and and accuracy with the model depth, and the training data set is um, kinetic data set. So this accuracy is validation set. So this accuracy, the average accuracy of the 3D resonate over top 1 and top 5 on the kinetic validation set. So here you looking at ResNet 18. Here we are getting accuracy till 66, and using kinetic datasets, and increase the model depth here. So ResNet 34, right? ResNet 34 we are getting here 70, around 70, more than 70, that accuracy. And resonate 50 is slightly more, resonate 101 slightly more, and resonate 152 we are getting around 73%, 73.73, 73 accuracy. And here more than 152 to 200, that is saturated, means here model is overfitting here. So a same result we found if we increase more than 150. So this is the graph if we create the shallow network, more depth, and how kinetic data set will work. So I'm showing another example also. Before that, I'm going to discuss about the 3D ResNet. the ResNet, what kind of the ResNet network is available, and what ResNet network used for, especially what we are going to discuss about it. So the basic ResNet, in the basic ResNet, there are two convolution layer. F here is the number of the filters, and so, and this is the residual connections, and this is the basic networks. Another is the bottleneck network. In bottleneck network, there are three convolution neural networks with this filter size, and here think about three base normalization, two ReLU here, and another is the change for this is the pre-act resident networks, and difference is the number of the channels, and they are making more channelized. Another is ResNet XT. ResNet XT, they are creating more grouping the features. You are looking here, more grouping the features here, and the number of the filters here, and here the dense network. For the creating the dense network, they are making more channelized here. So 128, 32 channel they are creating, and filter size is 3 to 3 into 3 into 3 for this layer. So here they are using two convolution layer, and here they are three convolution layer, 333 and 2. And this is one block. So one block, one net. So it's concate to next block, next block, next block, like that. So it creates kind of the layer. Another way I can show example how the network will work here. Here you looking at a convolution layer first, convolution 2x, 3x, 4x, 5x, and this is block, which block like bottleneck block, here pre block, here resonant XT block, and dense net, and this kind of the block. So in resonate, like in resonate in basic block, like we discussed about like number of the layer 18 in 34. So basically they are using 1834, and F here number of the channels, and is the features, and here channel. So for first convolutions, output number of channels 64s, and here output number of channels 128, and again the number of the this is the filters, and number of channel 256, and slightly number of the channels increasing, and because depth is increasing, and residual network making the training very cool. For similar kind of what difference you are getting here. So for example, dense network, for in dense networks, the size of the filters, the changing, because if you increase the size of the filter, then we convolve more. Convolve more, yeah, we are losing some information, we can but convolve more. So in 12 to 24 48, right, and here 36 for RX external. So you can see more about the paper also, so more discussion about here, but this is kind of the networks that build, and its GitHub repo also is available. The next is I want to show here. Then we discussed about the networks and how network working like that, and now we discuss about analyzing of the training of each data set. So I discussed different kind of data sets like UCF 101, HMDB 15, 18, 18 kinetics. You're looking here like this is number of the epoch, and this is the cross entropy loss. So if you are increasing epoch, and you watching that validation loss not decreasing after few epochs, and training loss decreasing. So what happened here? It's after few epochs using UCF 101 dataset and the resonant 18 network. It's not like 152 network. This training on resonant 18. So this complete experiment done on resonant 18. So resonant using the resonant 18 with a different kind of the dataset. So first dataset we are getting that validation loss not decreasing after few epochs, means it's overfitting happened here. So this model using this dataset resonant 18 overfit. Similar kind of HMDB dataset with ResNet 18, it's also overfit, and it also after few flow, and same kind of activity data set resonate in overfit because resin validation loss not decreasing. But in using the ResNet 18 in kinetic dataset, we found that validation load is still decreasing more, and training loss to also decreasing, but the validation also decreasing. Means model still learning something. So is the model here not overfitting? Model is still learning. This graph showing that we can go more deeper. So this experiment make the network better, and generate the thinking about that we can go more deeper. So the training using ResNet 18, we found that kinetic data set we are not overfitting here, but ActiveNet, HMDB, and USIP data set already overfitting. So using the deep data set, we can't train from the scratch. So if we training from the scratch using these three data set, it's not possible to train 3D CNN, 3D networks. But using the kinetic data set, we can training and we can go deeper also. So the kinetic data set enable the 3D CNN, enable the training for the 3D CNN deeper. So in the next experiment we found, I will show the next experiment. See here, in Resonate 18, we found 66 average accuracy. If we thinking about top 1 and top 5. So 66 average accuracy, after that, model will go overfitting. Then another experiment we using the 34, we are we reached 71 accuracy, but still model overfitting, right? And not shift using kinetic dataset. So these experiment done in kinetic dataset with a different kind of the network. So this is the different kind of the method, and we are getting the accuracy using the kinetic dataset. So in the kinetic dataset, 50 we are increasing the accuracy. So we are going the deeper here, and we are increase the accuracy. But you find here till 152 we are getting the average accuracy 737.7, and after that we increasing the more deeper, then same accuracy we are getting. So what we are getting here, if more deeper 200, yeah, one more deeper to 152 with kinetic dataset model or 50. So here we are getting orphaned with connected research. So you will find in ImageNet, if we comparing with ImageNet dataset for the image classification task for object detection like that, same kind of the accuracy we are getting for that also, and same kind of the graph we are getting for that also. So if you're thinking about ResNet with ImageNet, right, for 2D, 2D in the 2D CNN, the same kind of the history we found in 2015, same kind of history, and here the retrace history using the kinetic data sets, same kind of like 152 layer, and we are getting the accuracy. So these kind of the experiment done with different kind of the networks. Another network also we tried from this case like ResNet 200 Preact, that is the Preact, that is the Preact network. So same kind of accuracy we are getting, and this is the different white ResNet 50. We slightly increase the accuracy, but there 50 that's saturated, and XNet 120 layer, DenseNet 121 layer, 120 and 200. 121 and 200. What is the difference here? The slight difference here in accuracy, but 201 again it's saturated. So we are getting means what it's showing here the kinetic using the kinetic data set, it's connected enable the training more deeper using resonate. And another methods like we discuss about resonate, but another method like CNN, LSTM, into stream CNN, C3D, and Inception 3D, right? So using Inception 3D, we are getting 78% accuracy, and two stream I3D, that is another inception 3D model. So we are in 80% accuracy. So the inception also inceptions the that's in image also inception very deeper networks for the ImageNet also, the and we are getting the best accuracy in ImageNet. Similar kind of the accuracy we are getting here. ImageNet. Same kind of the accuracy we are getting for the RGB I3D network. For I3D means inception network also. So that is the best experiment the guys did in this paper. So what is the conclusion of this kind of the preparation and this kind of experiment, that we conclude that right now the public data set like kinetic data sets, it's useful for training in action recognition, human recognition, video classifications, like that. So another experiment did for the fine tuning also. For example, we use, for example, we use kinetic data set pre-trained model. So you heard about transfer learning, right? So transfer learning, what we did, we choose already whatever checkpoints we have pre-trained models, and we fine tune last few layers, right? We last few layers. So similar kind of experiment done with already pre-trained kinetic models to kinetic models. So here already pre-trained resonant 18 kinetic model, and if we fine tune last layer like last last convolution layer and last fully connected layer. So if you fine tune that layer using UCF1, then we found greater accuracy. In HMDB, we found 551 accuracy. Similar for train model on 34 kinetic model, and we fine tune this. We are getting greater accuracy. So this is table showing if we fine tune the network on the pre-trained models, then we can get significant results. For example, in the particular manufacturing industry, so in manufacturing industry, they want to find out human activities in the manufacturing plant. So, but if they want to build their models, they don't have such kind of the data for train this craze. But they have the few hours of the data like UCF, like SMDB, like that. So first, we can choose the kinetic free-trained models, and we can fine-tune that model fine-tune the model whatever we have real-time data like manufacturing industries recorded data. So from a few hours of data we have, then we can fine tune last few layers like that. So this kind of the successful history we found, and you hear the result around less than 80%. Like previously you find that 73% kinetic, the 73 that result, meaning around 70% result we found average accuracy here. But with the fine tuning with these networks, and that we are getting very nice and very significant and results like till 90% accuracy here getting user fine tuning. So that's enabling the fine tuning with the kinetic data sets. So it is proved that the kinetic data set, using the kinetic data sets, kinetic data set, the spatial-temporal third-dimension kernel can retrace history of the 2D CNN and ImageNet. So that is the main thing here. And I'm showing here one demo here. I'm showing demo to you, a video demo, how action recognition will work. So action recognition, action recognition. I will show the demo video. Yeah, I made the inference. I will show you the demo. Yeah. So I show you the demo. I think demo not coming. So wait for this stop server. Will come to the network. So I will show you demo again, sharing the screen again, and I will show you no. This way I will show entire screen. I choose entire, but you find the demo also. So this is the demo I show you. I'm going to open the presentations. So right now, I will explain the inference and training and these kind of things. So I will show you the repo. This is the repo. This is a very nice repo. You will find 3D resonance with acceleration. I share the link also, and very explained and very nice repo. And here, like you can enable whatever you want to experiment with resonate 15, 101, 151, 200, whatever. You can experiment here, and there available pre-activation resonate also, this also, this also, this also. So you can use here, and you can download the pre-trained model from here. You can click here, you will download the pre-trained networks, and this like 18, 34, and you can see the difference, the result, these pre-trained networks manually. You can see, and if you want to transfer learning your model, so for example, you want to transfer learning your model, so then you can use your model for the transfer learning. You have your data set, like you have many metrics entries, you have some action recognition in your company. For example, store action recognition. If you're in retail markets, then you can choose this kind of data set, find retrain model and fine tune your few layers. So you can use this also, and right, and same I show the performance how it works. So for installation, you need PyTorch. You have to install Conda. You have to need Coda 8, and you can install it. It's very simple if you are already Python guys. So, and you need FFmpeg for decoding library, for frame extractions, for frame like that. So this guy use FFmpeg and frog library. So you can use this library. That's good way, and different kind of the, and for downloading the network also, like ActiveNet, Kinetics, and UCF10 and HMDB. So these kind of the data sets link is here available. Official crawler is available. You can download here from the dataset if you want to train for scratch, but I'm not I'm not proposing you to download the dataset and start from the sketching because you need more computing power. So if you need rest of the GPUs for training kinetics, right? So I prefer you have your data, then you do transfer learning and you fine tune your data. So transfer learning steps, fine tuning, and these stick steps we will go through in the next level of the meetups like 02, like ResNet for accent recognition 01. This is the meetup. Second, ResNet accent recognition 02, that well explained for the fine tuning. I will come with, but this is the journal. You download it, and very simply you have to pass your parameters, your checkpoints, your query size, your number of class, how many class you want to identify, and you can start, you can train your model here. And very basics. Another thing I want to show you, that is for the training pipeline. If you want to go through for inference, you want to infer your pre-trained model, then go through this repository. This is a repository special for training purpose, and this repository is special for the inference purpose. Both repository I will share you on the meetup link and YouTube link also, so you can find it, and you can install Kudait and just Eligibility library, and this is your put your video here and download pre-trained model from here. You have to download pre-trained model from here, and you download your video here, and just infer. You have to just your mode like you have to need training mode, yeah, inference mode, your score mode. So you set your mode for score means you want to infer. You set the score mode. If you want score mode, if you want score, if you want to score mode, so then you can do it here, and so that is inference pipeline. I'm showing here inference pipeline. So that is all about today I'm going to tell about it. And what is the next? What next here? I'm going to show you next uh, 3D refraction 02. It will come with agenda, proper code, coding, part of especially coding. I will well explain code, and for training for inference purpose, I will explain well, and that is the next part. I will, if you're interested more, you can suggest me, and if you have any questions, hang it out, directly discuss, can mail. This is my mail ID, Gmail ID, directly mail me any questions. And I found this reference. This video is available, so you can write both. This is first for training for inference, and this is the research paper I'm showing here. So these great things. Now I'm going to stop my screen sharing, and thank you guys. If any inputs, any you like something, any suggestions, comment it me and mail me directly. You need any meetups and any other video that you're interested. I especially work on in video side and voice side, so I can, like, if PyTorch tutorial, anything you want, you can suggest. We can. So thank you guys. Thanks for watching this video.